Welcome to video lecture B8. This one is on coordinate systems and isomorphic vector spaces. I'll be your mentor, Tom Roby, and here are the outline and objectives. We'd like to harness this notion we have of B coordinates for vectors in arbitrary vector spaces to show that to show something called linear isomorphisms between different vector spaces. So it's a way of thinking about a vector space using a different set of eyes that help you see things in a different way. And in particular, if we've got a vector space of any sort and it happens to have a basis of cardinality n, then that vector space is actually isomorphic to r to the n. So that's something that we'll find quite useful. In the previous video lectures, we talked about B coordinates, but we were mostly working within the context of different coordinate systems for Rn itself. And now we'll look at other examples like polynomials and matrices, other examples of vector spaces. Okay, so here's the main theorem, which is that suppose I've got a basis with n things for v. Then I can think about this mapping that takes a vector x. So if x is in the vector space, then I can always write it in terms of the basis. That's what it means to be a basis. And in fact, there's a unique way to write it. And so then I can just say, well, what are those coefficients on the basis and make those the coordinates. That's the coordinate mapping. And what I claim is that this is a linear transformation from the vector space V to r to the n, which is 1-to-1 and onto. So it's just a map that sends everything to a unique thing, and everything over here came from a unique thing over there, and it's the nicest possible kind of map. So here's an example. P2, the polynomials of degree less than or equal to 2, has a basis 1t squared. That's the standard basis. And so you can write any polynomial in terms of it. So g of t is c plus bt plus at squared, and that maps to what I would call cba, which is in R3. So what I'm doing is I'm taking the space of polynomials and I'm saying that it's isomorphic to just R cubed, three-dimensional Euclidean space. Now suppose I had another vector like this. H of t was f plus et plus dt squared. Then what would the p coordinates be of g of t plus h of t? So this is the key point here, is that we want to understand how this map works. So if I know that, so over here in V, I have g of t, right, which is c plus bt plus at squared. Okay? And that maps over in R3 to this vector. Okay? And now h, so let's see, this was g and this was h. H is just f plus et plus dt squared, and that maps to f e a, f e d, right? So now what happens if I add these things? Well, if I add these, then I just get c plus f plus b plus et plus a plus d t squared. And since every vector in V has a unique representation in terms of a basis, this is the only representation that makes sense. And where does that map to? Well, it just maps to the vector in R3, c plus f, b plus e, a plus d. But this vector is just the sum of these two vectors. So adding these two vectors, so the point is that adding the two vectors here corresponds to adding the two vectors here. And so that's what it means to be an isomorphism. It means that morphism means shape, and isomorphism means that these two things have the same shape, and that we preserve the shape, meaning we've preserved the operations, which are what matters in a vector space. Okay. Similarly, if I rescaled this vector, I multiplied it all through by k, well then I just have kc plus kbt plus kat squared. Here I'd have kc, kb, ka, and so the correspondence works with that too. So that's what we mean when we say that it's a 1-to-1 and onto linear transformation, which is something that we call an isomorphism. Now, it's interesting to note that P2 has a different basis, which I'll call Q. Namely, Q1 of t is just the constant polynomial 1, and then I could have 1 plus t, and the third one could be 1 plus t squared. And I could say, well, what are the q coordinates of this thing? right? The p-coordinates of this are just 2, minus 5, 3, that column. But so if I want the q-coordinates, so let me just write something down here now. So I'm interested in the polynomial 2 minus 5t plus 3t squared. Now, if I just look at it in the standard basis coordinates, the p-coordinates, then I would just get 2 minus 5, 3. And I'll write a little script p there that you know. But what's it going to be in these other coordinates? Well, you can sort of see, right, that if I have to get this 3t squared somehow, right? And there's no t squareds in either q1 or q2. So I have to use q3 to get the 3t squared. So that means that when I'm thinking about this, what this is going to be in q coordinates, well, I'm going to have a 3 down there. Now, because I have a 3, that means I have 3t squared plus 3t plus 1. Now, I need to get a minus 5t. I already have a 3t. So in order to, what I'm going to have to multiply the q2 by is a minus 5. Okay? And then for the last step, how do I get the right constant term? Well, I've got 3 as a constant from the first one, and then I've got minus 5, so that's minus 2 total from that one. And so now this one, if I have 3 minus 2, I need to get 2. So it looks like, hang on, I did something wrong. So let's see. I have 3 here, and I need to get minus 5. So that means this needs to be minus 8. There we go. So this is I need minus 8 because then I'll have 3t squared plus 3t. But now here I'll have a minus 8t. And now my constant term will be 3t minus 8. So 3 minus 8 is minus 5 total, but I need to get 2, so I need a plus 7 coefficient on that. So the thing to think about is that what this is telling you is that this is how many copies of Q1 I have, this is how many copies of Q2 I have, and this is how many copies of Q3 I have. Just like here, I was how many copies of P1, P2, and P3. Now you might say, why would you ever want to use a different basis than the standard basis? And the answer is that it comes up all the time. Depending on what application you're doing or what your matrices look like, it's very convenient to be able to look at things from different points of view. So the point is this single polynomial in P3 can be represented in the obvious way, 2 minus 5, 3, in terms of the standard basis. But in terms of this less standard basis, it's 7 minus 8, 3. And if I had a wackier basis, it would be even trickier to figure out what these coefficients are. Because this basis is kind of triangular in some sense, it's easier to deal with. Okay? Okay, so suppose I've got two vector spaces, V and W. If I have one of these special one-to-one and onto linear transformations, phi from V to W, then I'll call phi an isomorphism, which, as I said earlier, is Greek meaning same form, and say that V is isomorphic to W. And we'll write this as a kind of equality or congruence. V is congruent to W. It means that for all practical purposes, these vector spaces are the same. There's a translation. It's like, you know, one of them is speaking English and one of them is speaking German, and you can just translate, you know, any English sentence into an equivalent German sentence or something. So the above theorem showed that if I have a basis with n elements, then V is isomorphic to R to the n, because that coordinate map just says exactly, you know, you've got your basis with n elements, you take the coefficients, you put them in there, then you're in R to the n. So any vector space where I'm allowed to use my scalars are allowed to be R is isomorphic to R to the n. So now let's look at some examples. What would P2 be isomorphic to? Well, so P2 we saw had the basis 1t squared, so it's actually isomorphic to R3. So what do you think that in general P sub d, polynomials of degree less than or equal to d, would be? Right? They should be isomorphic to R to the d plus 1. How about 2 by 2 matrices? If I have 2 by 2 matrices, then we saw earlier that one basis for that is something like 1, 0, 0, 0 and 0, 1, 0, 0. All of the places you can have a 1 in each of those spaces and then zeros everywhere else. So that means it'll be isomorphic to R4. Okay? In general, Rm cross n should be isomorphic to matrices, m by n matrices, should be Rm to the n, right? And so all I'm saying is that, right, a basis, for example, for R2 by 3 has as a basis 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0, 0, 1. So those six vectors in the vector space R2 by 3 are such that if I want to get any matrix, 2 by 3 matrix, I just say if I want an A here, I have A times this, plus B times this, plus C times this, plus D times this, plus E times this, plus F times this, gives me the matrix A, B, C, D, E, F. Okay? How about the next one? So if both of these guys, so P3 would be isomorphic to R4, but R2 by 2 is also isomorphic to R4. So polynomials of degree less than or equal to 3 is a 4-dimensional vector space. It's isomorphic to the 4-dimensional vector space R2 by 2, where I have 2 by 2 matrices, just because they're both isomorphic to R to the 4th. And there can be many different isomorphisms between isomorphic vector spaces. So as we saw, P2 has the basis 1t squared, and it has the basis 1 plus t plus t squared. And either way, PT is isomorphic to R3. But for example, if I write something in p coordinates, so like 1 plus t squared, in p coordinates that's 1, 1, 1, but in q coordinates it's just 0, 0, 1. So that's what can happen, is that you have these isomorphisms, but there's not a unique way necessarily of doing it, and basically it depends on what you choose as your basis. So you choose one basis, you'll get one isomorphism between polynomials in R3 or R4, and if you choose a different basis, then you'll get a different isomorphism. So I think that's all there is for video lecture B8. Thank you for your kind attention.